You don't see the real world. In fact, you never have your eyes, and more precisely, your brain are lying to you every moment of every day. In 2011, scientists at New York University made a startling discovery. When I perceive something is dangerous, my brain can literally make it seem closer than it really is. And in January this year, researchers at the University of California uncovered another illusion. My vision isn't live, it's delayed. Stuck up to 15 seconds in the past, as if my brain needs to buffer reality just like a YouTube video. From the time I was young, I was told never look directly at the sun. And yet those who dare, perhaps catching the fleeting beauty of a sunrise, see a warm golden orb climbing into the sky. But here's the twist. That golden glow is not the sun's true color in space. Without Earth's atmosphere, the sun would look pure white, a perfect blend of all visible colors. So why does it look yellow or red from here? It's a trick of the air. Molecules of nitrogen and oxygen scatter blue light away, leaving the warmer tones to reach my eyes. And even that white color in space is another illusion. Objectively, the sun emits more green photons than any other color. If my eyes worked differently, the sun would be green, but my brain takes all those colors, blends them together, and calls it white. So the sun I think I know is already a fabrication of my own mind. And that's not the only deception. The sun is constantly bathing me in light I cannot see. Ultraviolet rays invisible, yet they burn and tan my skin. Infrared waves, I can't see them, but I feel them as warmth on my face. Radio waves, long invisible pulses of light detected only by technology. My eyes evolved to see just a sliver of the electromagnetic spectrum. The rest of the universe is hidden, but the deception goes even deeper. Beyond light, the sun produces a flood of mysterious particles, so elusive that for most of human history, I didn't even know they existed. They're called neutrinos, ghost particles. Every second, trillions pass through my body without leaving a trace. They barely interact with matter at all, and yet they may be the key to answering one of the most profound questions. In science, what happened before the first light of the universe? The oldest light I've ever seen, the cosmic microwave background, is from 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely. My telescopes can't see past this wall. It's an opaque barrier, but neutrinos could pass through it. By studying these ghost particles, scientists may be able to map the universe as it was, not just in its first year, but in its first second, to peel back the veil of time itself. To see creation as it truly happened. The truth is, my vision is a tiny keyhole looking onto a vast, hidden universe. The reality around me is flooded with colors I'll never see, particles I'll never feel, and events I'll never directly witness. My brain is constantly editing, reconstructing, and even inventing the world I believe I'm experiencing. In other words, I don't live in the real world. I live in a rendered version of it. And perhaps knowing that will make me wonder what else reality is hiding. Imagine a Boeing 747, one of the world's most iconic aircraft, with a massive hole cut in its side and a 17-ton telescope installed inside. Peering into the cosmos, it sounds like science fiction. But it's real, Sophia. The Stratospheric Observatory for Infrared Astronomy. Why go to such lengths? Because Earth's atmosphere blocks most infrared light, the very light that reveals newborn stars and the hearts of distant galaxies. To see this hidden universe, astronomers must rise above the water vapor that absorbs infrared radiation. Space telescopes like James Webb are powerful, but expensive and hard to upgrade. Sophia offered a unique solution, a flying observatory that could chase celestial events around the globe. With instruments that could be swapped and upgraded between flights, it bridged the gap between ground and space, opening a new window onto the infrared universe. Sophia's mobility and adaptability made it a powerful tool for discovery. It allowed scientists to study cosmic phenomena in real time, from star formation to the chemistry of distant galaxies. More than just a telescope, Sophia was a testament to human ingenuity, proof that if the mountain won't come to Muhammad, we'll build a flying observatory to soar above it. It changed how we see the universe, revealing what was once invisible. Sophia's legacy is a bold statement. We will always find a way to see what's hidden. The universe is full of secrets, and with the right tools, we can uncover them. The sky is not the limit, it's just the beginning. Transforming a 747 into Sophia was an engineering marvel, Engineers designed a 16-foot door that could open mid-flight, exposing a 2.7-meter telescope to the stratosphere's harsh cold. The telescope was mounted on a spherical bearing, isolated from the plane's vibrations, and guided by a system making thousands of adjustments per second. This allowed Sophia to focus on targets with incredible precision, even as the aircraft sped through turbulent skies. Inside, scientists analyzed data in real time, exploring the hidden universe in infrared. Sophia revealed star formation, mapped the Milky Way's center, and even detected water on the moon. It was a flying laboratory, offering flexibility and clarity unmatched by ground or space telescopes. Humanity's curiosity drives us to build tools that extend our senses beyond nature's limits. Microscopes revealed the world of the very small telescopes. The vastness of space, these inventions shattered our sensory bubble, showing us that reality is layered and complex. Each new instrument, radio telescopes, particle accelerators, unveils another layer of the universe. But some mysteries, like the elusive neutrino, require entirely new kinds of detectors. Neutrinos are nearly invisible, passing through matter almost undisturbed. To detect them, we need massive sensitive instruments. New eyes for a hidden world. The quest to see the unseen is a journey into the unknown, pushing the boundaries of discovery. Trillions of neutrinos pass through your body every second. Yet you feel nothing. These ghostly particles stream from the sun, exploding stars and nuclear reactions, carrying secrets from the universe's most violent events. Neutrinos have no electric charge and interact only via the weak nuclear force and gravity, making them almost impossible to detect. To catch even a few, scientists need intense sources of neutrinos and detectors of unimaginable size. It's like searching for a needle in a cosmic haystack, but the reward is immense. Neutrinos are pristine messengers, able to escape from the heart of supernova and the sun, revealing processes hidden from light-based telescopes. They offer a unique window into the universe's most extreme environments. Detecting them is a challenge, but it unlocks secrets unreachable by any other means. Neutrinos let us peer into cosmic furnaces, tracing the origins of the universe's most energetic events. They are the ultimate invisible messengers. The hunt for neutrinos is a quest to see the universe as it truly is. Through them, we glimpse the hidden engines of creation. The neutrino story began with a puzzle in the early 20th century: missing energy and beta decay. Electrons emitted from decaying atoms had unpredictable energies, defying the law of conservation of energy. Some physicists considered abandoning this fundamental law, but Wolfgang Pauli proposed a radical idea. An undetectable neutral particle carried away the missing energy. He called it the neutron, but Enrico Fermi later renamed it the neutrino, the little neutral one. For decades, the neutrino remained a theoretical ghost, an elegant solution with no proof. Pauli himself doubted it could ever be detected, yet the idea persisted, driving physicists to search for evidence. The neutrino was a beautiful answer to a fundamental mystery. Its discovery would open a new chapter in our understanding of the universe. For 25 years, the neutrino was just a theory, until Frederick Rains and Clyde Cowan set out to catch it. They needed a powerful source of neutrinos, so they turned to a nuclear reactor, which produces trillions of neutrinos every second. Their detector, filled with water and cadmium, was designed to catch the rare interaction of a neutrino with a proton, producing a double flash of gamma rays. Shielded deep underground, they waited for the telltale signal. In 1956, they succeeded. The double flash appeared when the reactor was on and vanished when it was off. They had caught the ghost. The news was sent to Pauli, who celebrated the confirmation of his once undetectable particle. The neutrino was real, and a new era of physics had begun. The impossible had become reality. Detecting neutrinos from space required a detector on a colossal scale, shielded from cosmic noise. The solution: IceCube, a telescope buried deep in Antarctic ice. Instead of mirrors, IceCube uses a cubic kilometer of crystal-clear ice, embedded with over 5,000 light sensors. When a high-energy neutrino collides with an atom in the ice, it creates a flash of blue Cherenkov light. The sensors capture this faint glow, allowing scientists to reconstruct the neutrino's path and energy. The thick ice filters out other particles, letting only neutrinos pass through. In 2013, IceCube detected the first high-energy neutrinos from beyond our solar system. This marked the dawn of high-energy neutrino astronomy. IceCube opened a new window on the universe, revealing cosmic events invisible to traditional telescopes. The Antarctic ice became our lens to the most extreme corners of the cosmos. Why go to such lengths? To capture ghostly neutrinos or hidden infrared light? Every particle is a messenger from the past, carrying the story of the universe's origins. Neutrinos, in particular, can travel through matter and space unimpeded, reaching us from the heart of supernova and the dawn of time. If we could detect the cosmic neutrino background, we'd glimpse the universe as it was 1 second after the Big Bang. High-energy neutrinos trace the universe's most violent events, supernova, black holes, and cosmic rays. By following their paths, we uncover the engines driving the cosmos. The quest for the unseen is a journey into the nature of reality itself. Each discovery expands our perspective, revealing the universe's hidden beauty. The hunt for neutrinos is more than physics. It's a fundamental part of the human story. We look up, we wonder, and we build the tools to find answers. Right now, over 100 billion neutrinos are passing through your thumbnail every second, and you don't feel a thing. They come from the sun, from distant galaxies, from cataclysmic events that happened long before humans existed. They are everywhere and yet almost impossible to find. Catching a neutrino is like hearing the whisper of a nut. In the middle of a hurricane, if you lived your entire life waiting for just one neutrino to interact with you, the odds are about 1 in 25. Not terrible, right? And yet every second, 180 million billion neutrinos from the sun alone pass through Earth. Even if you built a wall of solid lead a light year thick, half of them would still pass through unhindered. The way particles interact is governed by 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity curves space-time itself. For a long time, neutrinos were thought to have no mass at all. Just like photons, electromagnetism shapes almost everything we see. But neutrinos are the ultimate neutral particle. No charge, no response. The strong nuclear force holds quarks together. Neutrinos ignore this completely. That leaves just one, the weak nuclear force. The weak force is why neutrinos exist at all. It lets particles decay and neutrinos slip quietly out like ghosts. But they're more than cosmic bookkeeping. They're messengers from the most extreme environments in the universe. On February 23, 1987, a star in the Large Magellanic Cloud reached the end of its life. Its collapse triggered a supernova. Hours before the light reached Earth, deep inside a zinc mine in Japan, a detector registered 11 neutrinos. Masatoshi Koshiba originally wanted to study German literature. A failing physics grade changed everything. The rest is history since then. Neutrino astronomy has joined other new ways of observing the cosmos. LIGO detects gravitational waves from cosmic collisions. Scientists It's only a matter of time before a single cosmic event is seen, in 3 ways at once: light, gravitational waves, and neutrinos. This will mark the dawn of multi-messenger astronomy, building a 3-dimensional understanding of cosmic phenomena. Neutrinos are hard to detect because they ignore almost everything. This makes them time capsules of the cosmos. In the vast ocean of the universe, neutrinos are the silent swimmers. They slip through matter, through planets, through you unnoticed, but in their silence, they carry the story of creation. For those patient enough to listen for a gnat's whisper in a hurricane, the reward is a glimpse into the beginning of time itself. They are the universe's quietest messengers, particles so small, so elusive, that you could live your entire life without one of them ever touching you in a way you'd notice, and yet they are everywhere. Even now, 100 billion neutrinos are passing through your thumbnail every second. They sail through planets, through stars, through you, as though nothing was there at all. Part 1. Why are they so hard to detect? To understand their ghostly nature, you must understand the rules of the subatomic world. The 4 fundamental forces. Gravity, the weakest force in particle physics, pulls together anything with mass. Electromagnetism, the force that governs our everyday world, binds electrons to nuclei, makes light, powers every chemical reaction in your body. The strong nuclear force, the muscle of the atom, glues quarks together to make protons and neutrons. And then there is the weak nuclear force, rare, subtle, and for neutrinos, the only force that truly matters, because neutrinos, unlike protons, electrons, or photons, are neutral in every sense. They are not made of smaller pieces. They feel no push from electric fields. Magnetic fields pass right through them as if they don't exist. The strong force irrelevant. Only the weak nuclear force and gravity can touch them. That is why a light year of solid lead would only stop half of them. Part 2, the day we caught the ghosts. And yet on February 23, 1987, the ghosts screamed 168,000 years earlier. In the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, a massive star's core collapsed. Its nuclear furnace went dark. Gravity crushed it inward until it could collapse no more. The star detonated a supernova, brighter than 1 billion suns. Hours before the light of that explosion reached Earth. Inside a zinc mine in Japan, 11 neutrinos struck Masatoshi Koshiba's detector. Kamio Kandai Toshiba, who once failed physics in school, had not even built his machine to catch neutrinos. He wanted to watch protons decay to prove the grand unified theory, but when protons refused to cooperate, he pivoted. He re-engineered his underground tank. 4,500 tons of ultra-pure water, surrounded by 1,000 light-sensitive detectors, into a neutrino observatory. 2 months after turning it on, he won the cosmic lottery. A 13-second burst of neutrinos passed through the Earth, messengers arriving before the light telling us the star had died. It was the dawn of neutrino astronomy. Part 3, Beyond the Cosmic Microwave Background. But what if we could go further? Today, the oldest image we have of the universe is the cosmic microwave background, the CMB light from when the universe was just 380,000 years old. Before that moment, the cosmos was a fog of charged particles, scattering photons in all directions. Light could not travel freely, but neutrinos, they escaped just 1 second after the Big Bang. At that moment, the universe was a blistering ocean of energy. 10 billion degrees Celsius. Quarks were binding into protons and neutrons. Antimatter pairs were annihilating each other in bursts of radiation, and neutrinos were colliding constantly with everything around them. But as space expanded and cooled, the collision slowed, and then suddenly the neutrinos were free. The universe was still opaque to light, but to neutrinos it had become crystal clear. If we could capture an image of this cosmic neutrino background, the CMB, we would have a picture of the universe at 1 second old. Part 4, the hunt for relic neutrinos. They are still here all around us, cooled by 13.8 billion years of expansion, streaming silently through space at nearly the speed of light. 300 of them pass through every cubic centimeter of the universe. We can't see them directly, but their fingerprints are faintly imprinted in the structure of the CMB itself, and in the distribution of galaxies across the cosmos. Direct detection, that's even harder. The Katrin experiment in Germany uses 20 micrograms of tritium, a rare form of hydrogen, hoping to catch 2 relic neutrinos per year. The Ptolemy project at Princeton wants to scale up to 100 grams of tritium, aiming for maybe 10 detections a year. So much effort for so little data. Part 5, why it matters. Why chase something so faint, so hard to find? Because if we could map the CMB, we could test our deepest theories about the birth of the universe and maybe rewrite physics itself. We could see past the wall of light into the first second of time, and watch the forces of nature, gravity, electromagnetism, the strong and weak forces, split apart and shape everything that exists. And neutrinos, these ghosts of creation, may one day let us do exactly that. We call them elusive, invisible, almost untouchable, but neutrinos have been here since the beginning. They stream through the first stars, through every planet, through every living being that has ever existed. They are the quiet witnesses of creation, and they are waiting for us to listen. In the universe, one law reigns supreme. Nothing can travel faster than light. Einstein set this cosmic speed limit 299,792,458 meters per second. Only massless particles like photons can reach it. Everything else falls short. But in 2011, the Opera experiment in Italy claimed neutrinos, nearly undetectable particles, broke this rule. Neutrinos are everywhere, streaming through us from the sun and distant cosmic events, yet they rarely interact with matter. The claim that they outpaced light threatened to append physics as we know it. Was Einstein wrong? Could the universe's most elusive particle be a cosmic outlaw? The world watched as science faced one of its greatest challenges. The stage was set for a high-stakes investigation. The Opera experiment fired neutrinos from CERN in Switzerland to a detector in Italy, timing their journey with atomic clocks and GPS. The result, neutrinos appeared to arrive 60 nanoseconds early. Faster than light, the physics community was stunned, but skeptical scientists worldwide raced to replicate the findings and scrutinize every detail. After months of intense review, the opera team found two errors: a loose fiber optic cable and a miscalibrated oscillator. Once fixed, the faster-than-light effect vanished. Neutrinos obeyed the cosmic speed limit after all. The episode was a powerful reminder science is self-correcting. Even the most shocking results must survive relentless scrutiny. In the end, Einstein's theory stood firm, but neutrinos had already proven themselves masters of mystery. Decades before opera, neutrinos sparked another puzzle, the solar neutrino problem. In the 1960s, Ray Davis Jr. built a detector deep underground to catch neutrinos from the sun. He found only a third of the expected number. Did we misunderstand the sun, or were neutrinos hiding something? For 30 years, scientists searched for answers. The breakthrough came with the idea that neutrinos might change flavors as they traveled if true. Davis's detector would miss the transformed neutrinos. The mystery deep in neutrinos weren't just elusive, they were shapeshifters. The Sudbury Neutrino Observatory in Canada was built to detect all three neutrino flavors. Its results were stunning. The total number of neutrinos matched predictions, but most had changed flavor en route from the sun. This phenomenon, called neutrino oscillation, solved the solar neutrino problem, but it also shattered the standard model, which said neutrinos should be massless. Oscillation meant neutrinos had mass, tiny but real. The standard model, once thought complete, was now incomplete. Physicists had to rethink the building blocks of reality. Neutrinos had quietly rewritten the rules. Their mass was a crack in our best theory. The universe had more secrets to reveal. The standard model explains mass through the Higgs field, but neutrinos are far lighter than expected. Their tiny mass hints at new physics beyond the standard model. Some theories suggest neutrinos are their own antiparticles, Majorana fermions. Others propose a seesaw mechanism with a heavy partner neutrino, making the observed one so light. There may even be a fourth sterile neutrino, invisible to all but gravity. Discovering it could help solve the mystery of dark matter. Neutrinos remain cosmic messengers, challenging our understanding at every turn. Their story is unfinished, pointing us toward deeper truths. By following their trail, we may unlock the universe's greatest secrets.